Hello everyone, I'm Thomas Beatrice and today I will present you my work that I show at PowerTech conferences at Belgrade. My work is about GPU optimization of endogenous peer-to-peer market with product differentiation, and all the name behind is all my supervisor from the SATI laboratory in France. So before talking about my work, I will talk about the electricity market. So nowadays the market is centralized. That means that all agents will send their production and their cost to a central agent, the system operators, and this agent will try to minimize the sum of the cost of production of each agent with the constraint that the production must be equal to the consumption. All computation will be made on a supercomputer, big server. But with the increasing number of agents in the market and the increased integration of renewable energy, researchers show that decentralization is a better way to solve this problem. So in the centralized market, all agents will talk with each other, and without any centralized agent, and we will try to minimize the sum of all agents and of all peers of the cost of each trade between agents, and the trade must be anti-symmetrical, which means that what is sold must be bought. And here the computation will be made on small computing units that each agent will have. But before doing that in the real life, we need to simulate how works this algorithm. And in this case, we have a case that the market is decentralized, algorithm is decentralized, but the computation will be made on one central unit, one computer, the scientific computer, which is not a supercomputer. And this must be done before any implementation, so we can't use the material computing unit of the decentralized market. But why do we need to simulate before implementing? The first idea is to size the new grid, the communication and electrical grid, to know how will be the future grids. We can use it also to tune parameters of the algorithm to be sure that it will converge and check stability and convergence of the algorithm. We will need also to compute over a long period of time to check robustness against extreme events, for example, tempest or high consumption. And we can say that microgrid is not the same that the actual grid, because the size is really not the same, and to know what will happen in the real grid, we need to simulate large cases over a long time. But with kind of algorithm, the computational complexity explodes with the number of agents and the number of lines of the grids. And for example, in Recherche, if we need 10 seconds to solve a 30 agent case, it will take 1 day to compute 1 year on MATLAB and CPU, but it's okay for a small case. But if we try to compute for 1,000 agents, it will take several years, but it's really not possible to use. So here we have a real important scientific computing lock, and my work is to enable simulation before operational deployment. So now I will talk about what is endogenous market computation, and I will show you some results and discussion before concluding. So here it's the peer-to-peer market. So we, as I said before, we try to minimize the cost of each trade, and the power of each agent will be the sum of their trade with all their peers. We call an endogenous peer-to-peer market when we take into account the constraint in the line during the market. So here we compute the power flow on the line thanks to the grid sensitivity with a DC power flow, and we will try to keep the power on the line behind a certain value. How do we do that? We solve the peer-to-peer market with the DMM, which is an algorithm, and each agent will minimize the cost function, send the trade to the peer, and send the total power to the system operator. The system operator will compute the DC power flow, transfer it to nodal price via an ADM, which is some kind of cost of using the grid, and send this price to the agent. We do it again and again until convergence. So here it's how can we make that in real life. It's one possible formulation, but it's not the only one. So here at the initialization, the system operator will send some information to the agent to help him converge. And during the computation, the peer-to-peer market will only send the power, and the system operator will send residual to show if it has converged, and the price. This formulation has the advantage to respect agent and peer-to-peer market privacy. The peer-to-peer market has already been optimized in my previous work. So in this presentation, I will only focus on the system operator optimization, and the system operator will only do matrix computation. So I will only talk about optimizing memory access, which is the most important in this case. So now I will talk about a little about GPU computation. So here we have the computation. So we have CPU will have serial code and will ask GPU to compute some calculation in parallel. The GPU has a lot of blocks and and a lot of threads in each blocks that will compute in parallel, and each block has one memory, which is called the chair memory, that is way faster than the global memory, which is the memory of the GPU. To have optimized GPU computation, we have two rules to follow. We must have coefficient memory access, which means that adjacent thread must access adjacent memory, and we need to use most possible the chair memory to prevent really slow memory access. Now we have a mathematical model for one array, and we ask how must we store this array in your GPU. We have two choices because the memory in GPU is one dimension, and we can store it in row major, is like that, and in column major, it's 3 times the same line, don't worry. And now that we choose how we store the matrix, we must ask what a blocks of thread must compute, a column of this matrix, a row, or a fixed number of data. If we give a color to each blocks, we can see this kind of repartition of memory access, and we can see that these two lines has no coefficient access. But with that, we cannot conclude in the on the better choice to make, because this choice may be faster if they use more shared memories. It is why to choose the best method to compute, I'll implement all configuration for all computation. I benchmark it with random data which are copied between each test, and different problem size with agent and line that varies, and I measure the time of computation. I kept the best method for the matrix and for the transpose matrix, and I compare the sum of the time for all computation. This gave me this kind of graph. We can see that at small size we have no difference between each graph, but at very big size we can see here a factor 2 between the computation time, and so we can conclude that at big size using the transpose matrix may divide by 2 the system operator computation time. Then I can show you some results on some cases of the global algorithm. So here I will show you the speedup on random cases, and we can say that with enough agent the GPU became faster, And at 900 agents, the CPU is really too slow to enable statistic simulation. It will take several days, so I can't show you the speed up at this number of agents. I also made simulation on fixed case, an open case, which is an open data cases, with 2,500 agents and 140 lines. And we can see here that for several steps in June, the GPU is 300 times faster. So we can conclude that the model size, the higher the speed up. However, I need to discuss about a really important point, is that some CDKs, for example in the European case, doesn't converge even with a huge number of iterations, even with the best tuning of penalty factor or algorithm parameters. So we can see here the simulation on all the months of June, and you can see here that 6 time step doesn't converge here. And 20,000 iteration, it means 20,000 communication between peers for one temporal step in real life, so it's clearly impossible to make it in the real life. So my illustration can be to change the algorithm or to reduce the precision asked for the power flow limit. But if we reduce precision, the power flow may be too high in the line, so I choose to add an offset on the limits. This offset must be not too high because it will be a suboptimal solution, but not too small because the constraint may not be respected. So here I compute for several values of the offsets, and we can see that with no offset or offset of 1 per unit, we have an overflow on a certain line. But with a offset of 2 or 5, it's okay. So to conclude, I realize the optimization, the analysis, and the implementation of an endogenous peer-to-peer market. The GPU is really faster and makes simulation possible at really huge size, but it shows that LGMs struggle to achieve high precision for this kind of cases on the power flow limits. And it shows that other decentralization algorithms with better convergence must be found or other management system. And in future work, I will do an endogenous market with an AC power flow to be able to be more precise and to take into account, for example, the voltage bound. Thank you for your attention, and this is my contact information.